Welcome to the second lecture of the second module, and we have been discussing the review of elasticity. As discussed in the last class, the focus of this lecture has been a brief review of 3D elasticity in general and introduction to anisotropic elasticity in particular. In our last lecture, we understood the generalized Hooke's law, that means the relation between the stresses and strains in terms of stiffness and compliance. Like we understood that at a point there are 9 stress components and corresponding 9 strain components, and therefore, they are related by stiffness or compliance matrix which has 81 elastic constants. Okay. But then we also understood that for symmetric stress and strain tensors, there are 6 stresses and 6 strains, and therefore, the number of elastic constants is 36. Okay. Again, from the energy consideration, we have showed that that there are the stiffness or compliance matrix is also symmetric, and therefore, the number of independent elastic constant because of the symmetry is actually 21. Okay. So, in the last class we understood this, and then we have actually introduced an important concept of planes of material property symmetry, and we saw that as a consequence of existence of planes of material property symmetry, the number of independent elastic constants are actually reduced. We have seen that based on the existence of number of planes of material property symmetry, the material could be triclinic or anisotropic. When there is one plane of material property symmetry, it is monoclinic. Then we have 3 mutually perpendicular planes of material property symmetry, it is orthotropic, and then we have isotropic material, which we all know. Okay. So, today we will discuss the engineering constants for orthotropic materials. Okay. First, let us see that for a fully anisotropic material, we have 21 independent elastic constants, and we have seen that out of this that some of these are extension stiffness, like S11, S22, S33 are the extensional stiffness. Then we have S44, S55, S66 are the shear stiffness. We also have extension coupling. Then we have shear extension coupling. We have shear coupling, meaning suppose, say for example, we apply only sigma 1. Okay. We apply only sigma 1 and no other stress, and all other stresses are 0. So, this will lead to all other stresses, say sigma 2, sigma 3, tau 2 3, tau 1 3, tau 1 2, all others are 0, only sigma 1 is not equal to 0. But as you can see from this stiff compliance matrix, you can see that because of the existence of sigma 1, there will be epsilon 1. What will be that epsilon 1? Epsilon 1 will be equal to S11 sigma 1. Okay. Because of the existence of sigma 1, there will also be epsilon 2. What is epsilon 2? S12 sigma 1. There will also be epsilon 3, S13 sigma 3. There will also be shear strain 2 3. What will be that? S14, sorry, this is sigma 1, S14 sigma 1. There will be also shear strain gamma 13, that is S15 sigma 1. There will be also shear strain gamma 12, that is S16 sigma 1. That means, all the strain components are there, but we have applied only one stress component, that too normal stress along direction 1. Okay. But that led to as a result of sigma 1, all the 6 components are present. That is why it is fully anisotropic. That means, when it is subjected to stresses, it will have if you apply stress, even if you apply a simple normal tensile stress in one direction, that will lead to tensile strain in that direction. In addition, that will be strains in the normal strain in the other 2 transverse directions, as well as there will be shear strain in all the faces. Okay. That means, each component of strains and stresses are actually coupled with all the stresses and strains, all the stresses and strains are coupled with each other. Okay. So, this is fully anisotropic. So, this is direct strain, this sigma 2 epsilon 2 is because of the extension coupling. We all know that is for we know that for conventional even for isotropic material, that is there because of Poisson's effect. Similarly, this is also because of extension coupling, and these are shear extension coupling. Okay. And there is also shear coupling, meaning, see, I have taken an example where only sigma 1 is applied. Similarly, if we apply only say one shear strain, that will lead to all the 6. If we apply only shear stresses in one plane, say tau 1 2, that will lead to all the 6 components of strains, 3 normal strains and 3 shear strains. So, even if we apply say shear stress in plane 1 2, that will not only lead to shear strain in plane 1 2, it will also lead to shear strains in plane 2 3 and plane 1 3, in addition to all the normal components of strain. So, these are the shear coupling. So, in a fully anisotropic material, there is extension coupling, there is shear coupling, there is also shear extension coupling. Then we have seen that for if there is one plane of material property symmetry, and say the 2 3 is the plane of material property symmetry, 2 3 is the, we have deduced that in the last class, plane of material property symmetry. As a result of this, out of these 21 constants, we could see that 4 of the shear extension coupling coefficients go to 0, 6 of these shear extension coupling coefficients go to 0. Okay. Namely, S 1 4, S 1 5, S 2 4, S 2 5, S 3 4, S 3 5. In addition, 2 shear coupling terms also go to 0. Okay. Namely, S 4 6 and S 5 6. So, total 8 terms from this compliance matrix become 0, leaving only 13 independent elastic constants. Okay. Then we have seen that if there are 2 mutually perpendicular planes of material property symmetry, okay, of course, we have seen that automatically guarantees that the third mutually perpendicular plane also happens to be a plane of material property symmetry. Therefore, when there are 3 mutually perpendicular planes of material property symmetry, what happens is all the shear extension coupling terms and all the shear coupling terms go to 0. All the shear extension coupling terms go to 0, all the shear coupling terms also go to 0, leaving only 9 independent elastic constants. So, what does that mean physically? If we apply only say normal strain along 1, like what we did for fully anisotropic, where we have seen if we apply only sigma 1, that leads to all the possible strain components, normal as well as shear. But in an orthotropic material, if we apply sigma 1, that will only lead to normal strain and no shear strain. Okay. of course, that normal strain will be in all the directions, because extension coupling is still there, okay, that is still there. So, that will lead to normal strain and no shear strain. Similarly, if we apply shear stress, suppose in plane 1 2, that will only lead to, suppose if we apply shear stress in plane 1 2, that will only lead to corresponding shear strain in plane 1 2, no normal strain and no shear strains in the other planes, because both normal shear extension coupling as well as shear coupling are 0. Therefore, if we have an orthotropic, suppose we have suppose this is an orthotropic material and it is actually subjected to, okay, only normal strain. So, as a result of this, there will not be any change in its shape, there it will be deformed, but all the rectangular faces will remain rectangular. Okay. There may be some contraction and expansion in the lengths, okay, but its shape will not change if it is subjected to normal strain, subject to normal stress, because there is no shear extension coupling. We know that the shear is actually responsible for distortion of the shapes. Okay. Now, natural question comes, the same is also true for isotropic material. Even in isotropic material, if we apply normal stress, that leads to normal strain, there is no shear strain. Then what is the difference? Difference is that in isotropic material, because of the normal stress is in one direction, the strains in the transverse directions are same, meaning if had it been an isotropic material, this S12 and S13 would have been same, but this is not same for an orthotropic material. That is the difference. In orthotropic material, there is no shear extension coupling, there is no shear coupling. In isotropic material also it is same, but in orthotropic material, the strains in the transverse direction, because of the application of strain in the longitudinal directions, are not same. Okay. Meaning the if we apply sigma 1, the strain along 2 and strain along 3 are not same, okay, which is same for isotropic material. So, then we have seen that out of the 3 mutually perpendicular planes of material property symmetry, one of these transverse planes may behave isotropically. When it happens, say for example, if all the fibers in a unidirectional fiber lamina are actually regularly spaced, then in this case, as shown in this figure, this 2-3 plane is the plane of isotropy, 2-3 is the plane of isotropy. Okay. And as a result of this, 4 more additional relations come into picture. That means, out of these 9 independent constants in orthotropic material, there are 4 relations. Okay. Like what happens is, as a result of this, S13 and S12 become same. Okay. Similarly, S33 and S22 become same, and in the 2-3 plane, S44 is actually a function of S22 and S23, and S55 and S66. So, these 4 additional constant comes, I mean they are actually dependent. Therefore, number of independent elastic constant is 5. Independent elastic constants. Okay. An example is regularly spaced fibers in an unidirectional lamina. Okay. So, and then finally, we have seen that if in an isotropic material where all the planes are planes of material property symmetry, we need only 2 independent elastic constants, and we are conversant with this. So, we do not need to discuss anymore. We have 2 independent elastic constants. Okay. So, we could see that due to the existence of planes of material property symmetry, the number of independent elastic constants required to characterize a material reduces from 21 in case of fully anisotropic material to only 2 in the case of isotropic material, and it has a significant importance in analysis of in solid mechanics, because you can understand we need only 2. When we need only 2 constants, life is far easier, and when we need 21 constants, definitely the calculations are more involved, the analysis is also more complicated compared to that for isotropic material. Okay. So, having understood that, today we will see what are engineering constants. Now, what all these discussions in the constitutive relations, that means we can, our objective has been to relate the stresses to strains. Okay. And the most I mean the simple way, the easiest way to write the stresses and strains, relation between stresses and strains are in terms of stiffness matrix. That means 6 components of stress are related to 6 components of strain, or in terms of compliance matrix. Okay. Now, that means to characterize a material subjected to stress, if we want to know what are the strains, we must know each element of the stiffness or compliance matrix. Okay. However, these elastic constants are actually not measured. Okay. Generally, they are not measured. So, the quantities which are actually measured in the laboratory are termed as engineering constants, and of course, there are relationship between the engineering constants and these elastic constants. The elastic constants are actually expressed in terms of engineering constants. So, for example, for a one dimensional simple rod subjected to load, if we want to know what is the deflection, we must know what is E, okay, and we know how to measure E, Young's modulus. So, those are engineering constants. So, Young's modulus, Poisson's ratio and shear modulus, these are the engineering constants, and we know they could be measured in the laboratory using universal testing machine. Okay. So, therefore, we will see for isotropic material, we know just by conducting a single experiment, we can actually determine the Young's modulus and Poisson's ratio, and the shear modulus could be expressed in terms of Young's modulus and Poisson's ratio. Similarly, we will see that for an orthotropic material, how these elastic constants could be expressed in terms of engineering constants. Okay. Engineering constants are those which could be actually measured in the laboratory. Okay. So, for example, if we take a simple tensile testing specimen, subjected to uniaxial, okay, in UTM, and we get the stress strain curve, and we know that the slope of this curve is E. Okay, is so if we apply along a particular direction, then Young's modulus in that direction is the applied stress longitude in that direction divided by the corresponding strain. Okay. So, the slope of the stress strain curve gives us Young's modulus. Okay. Suppose we apply in this direction, say this is 1, and we also keep a strain gauge along direction 2, okay, and we keep track of what is the strain along direction 2. Suppose the strain along direction 2 is this. Okay. Okay, I will draw a separate diagram maybe. Similarly, we can draw the longitudinal strain versus the lateral strain. Suppose this is the curve. I am drawing in this direction because generally for isotropic material, if the epsilon 1 is positive, epsilon 2 is negative, okay, for isotropic material. Therefore, I have drawn on the other side, and the slope of this curve is nothing but Poisson's ratio. Okay. Epsilon 2 by epsilon 1, okay, when only sigma 1 is applied. That is the definition of Poisson's ratio. So, in general, the slope of the stress strain curve gives us Young's modulus in a particular direction E I, which is given by sigma I by epsilon I. Okay. Sigma I is the applied stress and epsilon I is the corresponding strain in that direction, and the slope of the longitudinal strain versus lateral strain curve, that is minus epsilon j by epsilon I, when only sigma I is applied, is the Poisson's ratio. This is the definition of Poisson's ratio. Okay. Similarly, suppose we all know what is the definition of Poisson's ratio, that is lateral strain by longitudinal strain, but suppose you apply only sigma 2, all other stresses are 0, then because of this there will be a direct strain epsilon 2 and there will be a lateral strain epsilon 1. This is Poisson's ratio nu 2 1. So, note that nu 1 2 and nu 2 1 are not equal for in general. For isotropic material, of course, they are same, but that is why it is convenient to, it is important that we define Poisson's ratio like this, nu I j is equal to minus epsilon j by epsilon I. Okay. Now, for an orthotropic material, now we are actually trying to correlate the elastic constants with the engineering constants. So, using our knowledge of stress strain relationship, we know, suppose we have an orthotropic material and where, suppose you have an orthotropic material and we say for the time being this is x, y and z. Okay. Suppose these are the principal, I mean these are the planes of orthotropy, x plane, y plane and z plane are the planes of orthotropy. Okay. So, if we apply a stress sigma x, all other stresses are 0, what that will lead to? If we apply sigma x, definitely there will be a strain along x which is given by sigma x by E x. Now, because of the Poisson's effect, application of sigma x along x will lead to strains epsilon y. Now, going by the definition of Poisson's ratio, okay, what is the ratio of epsilon y by epsilon x is when only sigma x is applied, that is nu x y, this is the Poisson's ratio. Therefore, epsilon y is equal to minus nu x y epsilon x, and epsilon x is nothing but sigma x by E x. Therefore, this is epsilon y. Similarly, because of sigma x there will be a strain along z which is given by again in terms of Poisson's ratio nu x z. Same thing, only thing in case of isotropic material we have never distinguished the Poisson's ratio in that direction, but here the Poisson's ratios are different, x y and x z are different. Okay. And because it is orthotropic, definitely there will not be any shear strain subject, because it is only subjected to normal stress. So, the shear strains are 0. So, this is for a single stress. So, now we can actually extend this when all the stress components are simultaneously applied. Suppose in an orthotropic material, again we take that x, y, z are the planes of material property symmetry, mutually perpendicular planes of material property symmetry. Okay. Now, suppose it is first subjected to only sigma x. So, what will be the strain along x? Strain along x will be epsilon x by E x. Okay. What will be the strain along y because of sigma x? What will be the strain along y? Sorry, this is sigma x by E x. What will be the strain along y? Going by the definitions of Poisson's ratio, epsilon y is equal to minus nu x y epsilon x is equal to minus nu x y sigma x by E x. Okay. Therefore, this is minus nu x y sigma x by E x. What is the strain along z? Similar to this, nu x z sigma x by E x. Okay. Now, suppose we apply only sigma y. What is the stress along y? That is nothing but sigma y by E y. Now, sigma y along y will also induce lateral strain in x direction. What is that? Going by the definition of Poisson's ratio, minus nu y x sigma y by E y. What is the strain along z because of y? Minus y z sigma y by E y. Similarly, suppose we apply only sigma z. What is the stress? What is the strain along z? This is nothing but sigma z by E z. Because of stress along z, what is the strain along x? That is nothing but nu z x sigma z by E z. What is the strain along y? Because of stress along z, nu z y sigma z by E z. In addition, because we are dealing with an orthotropic material, okay, and we have assumed that the planes of orthotropy are x, y and z planes, which are mutually perpendicular planes. Now, suppose it is also subjected to shear stress along plane y z, tau y z. So, what that will lead to? In the y z plane there will be a direct shear strain gamma y z, which is nothing but tau y z by shear modulus g y z. Suppose it is also subjected to shear along tau x z. Therefore, in the x z plane it will lead to tau x z by g x z. Similarly, subjected to x y, it leads to tau x y by. So, this is an orthotropic material. Therefore, there is no shear extension coupling, there is neither shear coupling. Okay. Therefore, if we apply only shear strain along in the y z plane, that will lead to shear stress in the y z plane, that will lead to corresponding shear strain in the y z plane, and so is the case here also. Now, if this we have considered each of these stresses individually, now if they are applied simultaneously, we can use the method of superposition, and therefore, we can add this. This will give us the total strain. These are 0. Okay. Zero plus 0 plus 0, okay, 0 plus 0 plus 0 plus 0 plus this plus 0, these are all 0. Okay. So, we can superpose, of course, because this is a linear elasticity. Therefore, we can superpose the effect of all the individual stresses to find out what is the total strain. So, we could get what are the strains: epsilon x, epsilon y, epsilon z, gamma y z, gamma x z, gamma x y. Okay. So, we get a relationship for an orthotropic material between the stress and the strain. Now, if we write this in the matrix form and we get, okay, this is what we have just derived, okay, the stresses strains in terms of stresses, and this could be written in the form of matrix that the 6 components of strains are actually expressed in terms of 6 components of stresses by means of this 6 by 6 matrix. Of course, here the shear extension terms as well as shear extension coupling terms and shear coupling terms are 0. What is this? Actually, epsilon strains are expressed in terms of stresses by means of the compliance matrix. Therefore, this is the compliance matrix. So, what is this? Now, we can write this as S1 1 right. Similarly, this could be, this is S1 2 like this, okay. This is S2 2, okay. This is S3 3. So, we can write all this, okay. S4 4, S5 5, S6 6, S1 3, and you can see S1 4 1 5 1 6 because it is orthotropic material, these are 0. Okay. So, we could actually express elements of the compliance matrix in terms of engineering constants. What are the engineering constants? 3 Young's modulus E x, E y, E z, 3 Poisson's ratios nu x z, nu y z, nu x y, and 3 shear modulus G y z, G x z, and G x y. Okay. Therefore, this is what exactly these are the the compliance terms of the compliance matrix in terms of engineering constants. Now, what we have done here is, if you look at the previous slide, we have intentionally to, because we are convenient in the relation of stress strain in the Cartesian coordinate x y z. Therefore, up to this we have actually discussed the stress strain relationship with reference to x y z coordinates, but we have mentioned clearly that x, y and z planes are the planes of 3 mutually perpendicular planes of material property symmetry in an orthotropic material. Okay. Now, the planes of orthotropy are generally actually denoted by 1 2 3. Okay. Say this is 1. Say for example, if you consider a unidirectional lamina along the direction of the fiber, okay, this is 1, that means 1 is the I mean normal to the plane 2 3. Okay. So, this is the direction of orthotropy 1. Similarly, 2 is the other direction of orthotropy which is perpendicular to 1, 3 is the third direction of orthotropy. Okay. So, now generally this 1 2 3 are the planes of orthotropy. I mean 1 2 3 are the axes, but 1 means this the corresponding plane where 1 is the surface normal. Okay. So, these are the 3 perpendicular planes of material property symmetry in orthotropic material, and hence we write everything with respect to 1 2 3. Just replace this x y z by 1 2 3. So, this is now x y z conventionally we use for analysis axis or loading axis. Okay. Because whenever we analyze any deformable solid, we first if it is in the Cartesian coordinate, we first define the x y z. Okay. Sometimes this 1 2 3 may coincide with x y z, but not necessarily always. Say for example, if we have a lamina where the fibers are actually oriented in a defined direction, therefore, this is 1, 3 is same anyway 1 2 3, but if you look at this, this is x, okay, this is y, this is y, and z of course coincides with 3. Okay. Now, x and 1 are not same, they may be, they have a different orientation. Okay. Similarly, in this case this is 1, this is 2 and 3 is of course same, but your x could be this, your y could be coinciding 1 and Z is same. So, 1 2 3 when we write, these are actually the planes of directions of orthotropy. Okay. 1 2 3 are the directions of orthotropy, sometimes also called principal material direction. So, now we can write that S 11 is nothing but E 1. What is E 1? E 1 is nothing but the Young's modulus along direction 1, E 2 is the Young's modulus along direction 2, E 3 is the Young's modulus along direction 3, and similarly we have the Poisson's ratios and the shear modulus. Okay. So, these are the engineering constants. Okay. Now, as we have as we defined that engineering constants are those which could be actually measured in the laboratory. So, what we do, suppose you want to find out what is E 1, you take this lamina, okay, load it along this direction, we load it along this direction in UTM and determine what is the epsilon 1, and from this stress strain curve epsilon 1, from the strain gauge reading you get epsilon 1. So, you can find out E 1. Similarly, by loading along direction 2 we can get E 2, and henceforth hence we can get all these even the Poisson's ratios also could be calculated, but make sure that the relationship between Young's modulus and Poisson's ratio which we knew for isotropic material actually does not hold good here. Okay. So, now we know that the stiffness and compliance matrix are symmetric, therefore, S 1 2 is equal to S 2 1. So, they must be same, sorry, they are equal. Similarly, equal. So, in general S I j is equal to S j I for I is not equal to j, meaning S 1 2 is equal to S 2 1, okay. S 2 3 is equal to S 3 2, S 1 3 is equal to S 3 1, others are anyway 0, other off diagonal terms are 0, and this leads to a relationship which is known as reciprocal relations. That means, as we have discussed that nu 1 2 and nu 2 1 are not same, unlike isotropic material they are not same, but they are actually related by this relation. Okay. Nu 2 1 by E 2 is equal to nu 1 2 by E 1. Similarly, nu 1 3 and nu 3 1 are also bound by this relation. So, in general nu I j by E I is equal to nu j I by E j. So, this is the relationship between the Poisson's ratios. Please note what is nu 1 2 and nu 2 1. Suppose this is our direction 1, this is our direction 2. Okay. Suppose if we apply only sigma 1, then nu 1 2 is equal to minus epsilon 2 by epsilon 1. Suppose if we apply only sigma 2, then nu 2 1 is equal to minus epsilon 1 by epsilon 2, and they are related. Nu 1 2 by nu 2 1 is equal to E 1 by E 2. Okay. Where from this comes? Because the stiffness and compliance matrix are symmetric, therefore, we get this reciprocal relationship. Okay. Even though nu 1 2 and nu 2 are not same, but they are dependent and they are decided by the ratio of E 1 and E 2. Okay. So, in general nu I j by E I is equal to nu j I by E j. So, as we know that for orthotropic material we have 9 independent elastic constants. Now, we have actually expressed the elements of the compliance matrix in terms of the engineering constants, and therefore, we can write that for an orthotropic material we have 9 independent constants. These are 9 independent engineering constants. And these are 9 independent elastic constants, and we understood their relationship. So, in general we can write sigma is equal to stiffness matrix into epsilon, I mean and epsilon is equal to compliance matrix into the stress sigma. Okay. So, we understood the relationship between the engineering constants and the elastic constants. Now, we have actually derived the elements of the compliance matrix in terms of engineering constants, but now that the stiffness and compliance matrix are mutually invertible, okay, because inverse of S gives us actually C. Therefore, we can write the elements of the stiffness matrix in terms of those of the compliance matrix or vice versa. Okay. Now that we know now that we know these elements of compliance matrix in terms of E1, E2, E3, nu 1 2, nu 2 3, nu 3 1, G1 2, G2 3, G3 1. If we put those, we get the elements of the stiffness matrix in terms of the engineering constants. Okay. We could write the elements of the stiffness matrix in terms of engineering constants, okay, by these expressions. Okay. So, therefore, we obtain the relationship between the engineering constants and the elements of the stiffness and the compliance matrices. Okay. Now, we have 9 independent engineering constants or elastic constants. Now, there are some restrictions on those. What are those? Let us try to understand that. Before that, let us see, we just revisit the restrictions on elastic constants for isotropic material. We know that G and E have to be always positive, like if we apply a tensile stress, that will lead to a tensile strain, therefore, E must be positive. Same is true for G, and we have for an isotropic material the relationship between G, E and nu given by this. Now, if G has to be positive, E is positive, and if G has to be positive, then Poisson's ratio must be greater than -1. It cannot be less than -1. In that case, G becomes negative. Okay. Now, suppose an isotropic material which is actually subjected to hydrostatic stress. I think all of us know what is hydrostatic stress, equal stress in all directions. If you put an object under water, it is subjected to hydrostatic stress, okay, say sigma 1 or sigma say x y, sigma x, sigma y, they are all equal, and this is equal to pressure P. Okay. If it is subjected to hydrostatic pressure like this, then we know from our solid mechanics that the volumetric strain is given by P divided by this, where this K is the bulk modulus. It shows how much, because under the hydrostatic stress what is the change in volume. Okay. So, naturally K has to be positive, because if it is subjected to compression, its volume must decrease, and if it is subjected to hydrostatic tension, say in the case of balloon, so if it is subject, it inflates. Okay. Therefore, K must also be positive, and the fact that K has to be positive here from this expression, from this relation, leads to that the Poisson's ratio should be less than half. So, this is the restrictions of Poisson's ratio in an isotropic material, and we know that Poisson's ratio in an isotropic material cannot be more than 0.5, and it cannot be it has to be more than 1. Okay. So, we ask somebody to actually give us the values of Young's modulus and Poisson's ratio for a particular material, say steel, and he or she takes it to the UTM, measures it and gives us the result that Young's modulus is say maybe 200 megapascal, gigapascal, Young's modulus is 200 gigapascal, and say he tells you that the Poisson's ratio is 0.8. Therefore, you can immediately infer that there is some issue in the calculation or in the data acquisition. It cannot be, because we know that for a material like steel, the Poisson's ratio cannot be more than 0.5. Therefore, so this gives us an additional check on the measured properties. Okay. Similarly, there are restrictions on orthotropic engineering constants on orthotropic materials. Okay. again the philosophy is same for the first law of thermodynamics, that means all the diagonal elements of C and S must be positive. Okay. The argument is that just now we discussed that if we apply a normal stress along a particular direction, that must lead to corresponding normal strain. Okay. If we apply tensile stress, it cannot give to lead to compressive strain in that direction, therefore, they must be positive. So, we know that the elements of compliance matrix in terms of engineering constants, and therefore, in order to have the diagonal elements, I have only written the diagonal elements here to be positive. The condition is that this E1, E2, E3, G1 to G2, 3, G3, 2 must be all greater than 0. Okay. Similarly, if we write in terms of the compliance matrix in terms of these engineering constants, again only I have written the diagonal terms of the stiffness. Similarly, if we write the stiffness matrix in terms of the engineering constants, I have only written the diagonal elements of the stiffness matrix. So, each element is greater than I mean positive, each element is positive, gives rise to these conditions 1, 2, 3 and of course, this. Okay. So, let us consider say this condition 1 minus nu 1 2 into nu 2 1 greater than 0 and see what that leads to. Suppose 1 minus nu 1 2 into nu 2 1 is greater than 0. This means nu 1 2 into nu 2 1 is less than 1, which implies nu 1 2 is less than 1 by nu 2 1, and we know that nu 1 2 by nu 2 1 is equal to E 1 by E 2, which implies 1 by nu 2 1 is equal to E 1 by E 2 into nu 1 2. So, if we do this, this implies nu 1 2 is less than equal to E 1 by E 2 into 1 by nu 1 2, which implies nu 1 2 square is less than equal to E 1 by E 2, which implies nu 1 2 is less than under root E 1 by E 2. So, therefore, we get this relationship nu 1 2 is less than under root E 1 by E 2. Similarly, by taking other conditions like by considering this and these conditions, we get the other relations. Okay. So, we get these relations, that means there is a relationship, that means there is a interdependency. Even though we have 9 engineering constants, there are interdependencies between those constants. Okay. Now, what is the usefulness of this? These interdependencies are used to examine the consistencies of, just now we have told that suppose you actually take an orthotropic material to the laboratory and try to find out those 9 engineering constants. Once we get this for a large number of data, we must see that those values actually satisfies this interdependency to be consistent with the mathematical theory of elasticity. Okay. If it is not, then there is something wrong. Okay. Again, one important thing is that it is suppose say for example, for an orthotropic material, suppose Young's modulus along direction 1 is 180 GPa and Young's modulus along direction 2 is 10 GPa. It is possible. This is a typical example for a graphite epoxy lamina, unidirectional graphite epoxy lamina. Then you can see that nu 1 2, okay, nu 1 2 which is under root E 1 by E 2 could be actually greater than 1. Now, in our notion in isotropic elasticity, we know that the Poisson's ratio cannot be 1, it cannot be greater than 0.5, but this is possible in the case of orthotropic material. However, they have to be checked for other other interdependencies. It has to be checked for other, that this needs to satisfy the other conditions. Okay. So, this knowing these constraints in the engineering constraints for orthotropic materials. Once they satisfy this data, the material properties obtained from the laboratory could be used for design and analysis of structures with more with confidence, you know. So, what we have learned today is that what are the engineering constants for orthotropic materials. Okay. There are 9 engineering constants corresponding to 9 elastic constants, and we have also established the relationship between the engineering constants and the elastic constants, that means the elements of the compliance and the stiffness matrix. And finally, we also understood the existence of restrictions on the engineering constants for orthotropic materials, and those restrictions are useful to check the consistency, check the accuracy of the experimentally observed data from the laboratory. Thank you. I will continue in the next class.